Let's explore one of mathematics' most intriguing paradoxes: 0 raised to the power of 0. The first fundamental rule of exponents states that any number a raised to the power of 0 equals 1. This rule holds for almost any base value we choose. For example, 2 to the power of 0 equals 1. This makes sense when we think of powers as repeated multiplication. 2 to the power of 0 means we aren't multiplying 2 by itself at all, giving us the multiplicative identity, which is 1. Similarly, 5 to the power of 0 equals 1. In fact, we could use any non-zero number as our base, and the result would still be 1. Even a larger number like 100 to the power of 0 equals 1. The pattern is consistent. Any value raised to the power of 0 equals 1, regardless of how large or small that value might be. The second important rule tells us that 0 raised to any positive power equals 0. This makes intuitive sense. If you multiply 0 by itself any number of times, the result is always 0. For instance, 0 to the power of 1 simply equals 0. This is just 0 itself without any exponentiation. 0 to the power of 2 equals 0 times 0, which is still 0. The absorbing property of multiplication by 0 means that any product involving 0 will always be 0. And 0 to the power of 5 equals 0 as well. No matter how many times we multiply 0 by itself, we cannot escape the result of 0. Now, let's examine these two rules side by side. On the left, we have the rule that a to the power of 0 equals 1, which works for virtually any value of a. On the right, we have 0 to the power of b equals 0, which applies when b is any positive number. But now we encounter a genuine mathematical paradox. What happens when we try to evaluate 0 to the power of 0? We have two different rules that could apply, potentially giving us two different answers. If we follow our first rule, treating 0 as any other base a, then 0 to the power of 0 should equal 1. This follows the pattern we observed with all other bases. But if we apply our second rule, considering that our exponent is 0 and our base is 0, we might conclude that 0 to the power of 0 should equal 0, continuing the pattern for 0 raised to different powers. We've reached a contradiction. Should 0 to the power of 0 equal 0 or 1? Both answers seem plausible based on the rules we've established. This is what makes it a true mathematical paradox. To resolve this apparent contradiction, mathematicians have needed to develop more sophisticated approaches using limits, formal algebraic systems, and considerations from different branches of mathematics, like combinatorics and set theory. This conflict between two equally valid mathematical rules illustrates why 0 to the power of 0 requires special consideration. It's not merely about choosing a convention, but understanding the deeper mathematical reasoning behind why one answer might be preferable to another in different contexts. Let's examine patterns in exponents to understand why 0 raised to the power of 0 equals 1. This isn't arbitrary. It follows a logical pattern we can discover by looking at data. To understand why 0 to the power of 0 equals 1, we'll create a table to track how different values of x behave when raised to various powers. Our table will show x cubed, x squared, x to the first power, and x to the 0th power. Let's build our table row by row, starting with x equals 2. Remember, when we raise a number to a power, we're multiplying the number by itself that many times. So 2 cubed is 2 times 2 times 2, which equals 8. Notice that 2 to the power of 0 equals 1. This follows from the rule that when you divide a number by itself, you get 1. Since 2 to the first power divided by 2 equals 1, we can think of 2 to the 0th power as 2 to the first power divided by 2. Let's try a different value. When x equals 1.5, we see that 1.5 cubed is approximately 3.375, 1.5 squared is 2.25, and 1.5 to the first power is just 1.5. But look at 1.5 to the 0th power, it still equals 1, just like with our previous value. Now let's examine when x equals 1. Here we see something interesting. My 1 raised to any power equals 1. That's because multiplying 1 by itself any number of times still gives us 1. And yes, 1 to the 0th power still equals 1, continuing our pattern. What happens when our base is a fraction? For x equals 0.5, we see that as the power increases, the results get smaller. 0.5 cubed is 0.125, 0.5 squared is 0.25, and 0.5 to the first power is 0.5. This makes sense because multiplying by a number less than 1 makes values smaller. But remarkably, 0.5 to the 0th power still equals 1. Let's try an even smaller number. When x equals 0.1, the higher powers produce very small numbers. 0.1 cubed is 0.001, 0.1 squared is 0.01, and 0.1 to the first power is 0.1. The values are rapidly approaching 0 as our base gets closer to 0. However, 0.1 to the 0th power still equals 1, maintaining our consistent pattern. Now for the crucial observation, what happens as x approaches 0? We see that x cubed, x squared, and x to the first power all approach 0. This makes sense, since powers of very small numbers become even smaller. But looking at the pattern in our last column, x to the 0th power continues to equal 1, regardless of how small x becomes. Examining the entire rightmost column, we can see that for any value of x, x to the 0th power equals 1. This pattern is completely consistent across all values. If we follow this pattern to its logical conclusion, it makes sense to define 0 to the 0th power as 1, maintaining mathematical consistency. The blue arrows show how our values progress as x gets smaller and smaller, approaching 0. While the powers x cubed, x squared, and x to the first power all approach 0, x to the 0th power remains stubbornly equal to 1. This pattern preservation is why mathematicians define 0 to the 0th power as 1. There are other mathematical reasons that support this convention. For example, in combinatorics, there is exactly one way to select 0 elements from a set of 0 elements, and in polynomial expansions, defining 0 to the 0th power as 1 ensures that formulas remain consistent. The pattern we've observed is one of the most intuitive ways to understand why 0 to the 0th power equals 1. Let's explore how exponents can be understood through counting functions between sets. This combinatorial interpretation will help us make sense of why 0 to the power of 0 equals 1. Let's start with a concrete example using a set y with 2 elements and a set x with 3 elements. I'm drawing two sets, a blue set y with 2 elements labeled y sub 1 and y sub 2, and a red set x with 3 elements labeled x sub 1, x sub 2, and x sub 3. Let's explore how many different functions we can create that map from set y to set x. A function assigns each element in y to exactly one element in x. Here's our first possible function. Both y sub 1 and y sub 2 are mapped to the same element x sub 1. This is a valid function because every element in y gets assigned to exactly one element in x. Here's another possible function where y sub 1 maps to x sub 2 and y sub 2 maps to x sub 3. Each element in y is mapped to a different element in x. And here's yet another valid function where y sub 1 maps to x sub 3 and y sub 2 maps to x sub 2. How many total functions are possible? For each of the 2 elements in set y, we have 3 possible choices from set x. Using the multiplication principle, we get 3 times 3, which equals 3 squared, or 9 possible functions. Let's try another example with a smaller set y containing just 1 element, and set x with 2 elements. Here I've drawn set y with just 1 element y sub 1, and set x with 2 elements x sub 1 and x sub 2. The first possible function maps y sub 1 to x sub 1. Since there's only 1 element in y, we just need to decide where to map it. The second possible function maps y sub 1 to x sub 2. These are the only 2 possibilities. In total, there are 2 to the power of 1, which equals 2 possible functions. This makes sense because we have 1 element in y, and for that element, we have 2 possible choices from set x. Now let's consider something more interesting. What happens when set y is empty containing 0 elements, while set x has 1 element? I've drawn an empty set y with no elements, and set x with just one element x sub 1. This scenario might seem strange, but it's perfectly valid mathematically. When y is empty, there's exactly one function possible, the empty function. Since there are no elements in y that need mapping, the function doesn't map anything, but it's still a valid function. Applying our pattern, this gives us 1 to the power of 0, which equals 1. This matches the number of possible functions we found, exactly 1. This also aligns with the standard mathematical convention that any number to the power of 0 equals 1. Now for the most intriguing case. What happens when both set y and set x are empty, containing 0 elements each? Here I've drawn two empty sets. Neither contains any elements. When both sets are empty, we still have exactly one possible function, the empty function. Since there are no elements in y, there's nothing to map. And the function that maps nothing to nothing is a perfectly valid mathematical function. Following our pattern, this gives us 0 to the power of 0, which equals 1. Even though this expression seems undefined when approaching it from other perspectives, the combinatorial interpretation gives us a clear reason why 0 to the power of 0 should equal 1. This combinatorial perspective gives us a natural way to understand why 0 to the power of 0 equals 1. It's not just an arbitrary convention, it's the number of functions from an empty set to an empty set. This interpretation is just one of several reasons why mathematicians define 0 to the power of 0 as 1. It allows many mathematical patterns and formulas to work consistently without requiring special cases. Let's explore why mathematicians define 0 to the power of 0 as 1, a convention that might seem puzzling at first glance, but has solid mathematical reasoning behind it. Let's start with pattern analysis. For any non-zero value of x, x to the power of 0 equals 1. This is a fundamental rule in exponents. If we start with values close to 0 and observe the pattern, like 0.1 to the power of 0 or 0.01 to the power of 0, they all equal 1. This pattern suggests that as x approaches 0, x to the power of 0 remains 1. A more rigorous approach comes from calculus. When we examine the limit of x to the power of x as x approaches 0, we can prove that this limit equals exactly 1. This is significant because x to the power of x represents a different path to approach 0 to the power of 0, and arriving at 1 through this limit reinforces our convention. From combinatorial mathematics, the expression x to the power of y can represent the number of ways to map a set of y elements to a set of x elements. When both sets are empty, that is, when x and y are both 0, there is exactly one way to map, the empty function. This unique empty mapping is another reason why 0 to the power of 0 equals 1 makes mathematical sense. Perhaps most compelling is the argument for mathematical consistency. Defining 0 to the power of 0 as 1 makes numerous formulas work smoothly without requiring special cases. For example, in the binomial theorem, power series expansions, and the formula for derivatives of x to the power of n, setting 0 to the power of 0 equal to 1 allows these formulas to work seamlessly without exception. All these different mathematical perspectives, pattern analysis, limits, combinatorial reasoning, and the need for consistency independently point to the same conclusion. Defining 0 to the power of 0 as 1 makes the most mathematical sense. It's important to understand that 0 to the power of 0 equals 1 is ultimately a mathematical convention, but not an arbitrary one. It's a convention with strong mathematical justification. Mathematicians have chosen this definition because it creates elegance in formulas and prevents the need for special cases across various fields of mathematics, from calculus and combinatorics to algebra and analysis. Without this convention, many powerful theorems would require awkward exceptions. So while 0 to the power of 0 might initially seem ambiguous, the mathematical community has settled on defining it as 1 for very good reasons. 0 to the power of 0 equals 1. This convention allows powerful mathematical formulas to work without special cases, creating a more elegant and unified mathematical system. Remember, in mathematics, useful conventions are chosen because they make the broader system work better. And the convention that 0 to the power of 0 equals 1 exemplifies this principle perfectly.